Good morning po, sir.
Right, good morning, Mayan. Naririnig mo ako?
Opo, sir, naririnig
Okay,
po.
thank you. All right. All right. For today, we will be talking about the exercise 2 tutorial, which is about um it's about contaminant transport. Okay. So this is a topic about how the contaminants, once they enter the groundwater, how do they actually move around the groundwater? Okay. And the short answer here is that they simply follow the path of the groundwater. Okay, so they just flow along with the groundwater flow direction. Okay. And for that, let's talk about some concepts pertinent to our exercise. Media is a term which refers to soil and rock. Okay. Particularly soil or rock that can actually permit flow of water. Hence, your soil, most soils can permit flow of water. For rocks, it has to be either fractured or weathered. If the rock is too solid or too intact, it might not be able to permit the flow of water. So media is mostly soil and fractured or weathered rock. Seepage velocity is the 3D movement of groundwater through the pores of the media. Okay? As opposed to the Darcy velocity, this is just the net movement of flow from to a cross-sectional area. Okay. So I'm gonna expound this later on. Okay. Effective porosity, on the other hand, is related to the seepage velocity. Okay. So effective porosity by definition is the interconnected pore volume or voids that can contribute to the permeability. Okay. And then discharge is the volume of flow per unit of time. Okay. So volume per time. And then hydraulic conductivity is basically the ease of flow of a fluid to a media. Okay. The higher the hydraulic conductivity, the easier it is for the fluid to flow through the media. Permeability is more of the property of the media alone. Okay. This is different from hydraulic conductivity in a sense that hydraulic conductivity depends on the fluid and on the media. Okay. While permeability is basically just about the media. Okay. For hydrogeology and contaminant studies, hydraulic conductivity is more frequently used because this is more straightforward to use, and most of our calculations only involve flow of water through your media. And then hydraulic head loss is the difference between the topmost level of a water to a level being reckoned. And then flow path length is the shortest distance to be traveled by a flow. And then hydraulic region is basically hydraulic head divided by your flow path length. Okay, another concept is the anisotropy of your flow. Let's try to draw this one. Let's say we have two layers, let's say three layers. First layer is sand. Second layer is, let's say, silt. Third layer is also still sand. The anisotropy of flow simply states that the permeability or the hydraulic conductivity of your flow will depend on the direction in which your flow is going. Let's say you have, okay, so just a heads up, the hydraulic conductivity of sand is very high. Okay. While for the silt, it is very, very fine. So the hydraulic conductivity of silt is very low. Okay. So water cannot easily pass through silt. Okay. Now, if you have water flowing in this direction, it will easily flow through sand. Okay. We have a big arrow in there. And then once it reaches the silt layer, it will slow down. Okay. And the note that the flow of water has no other option but to traverse the silt layer, okay, if it's going perpendicular to the bedding. Okay. So all of them will have to pass through this silt layer first before it can travel through the third sandstone layer. Okay. Therefore, in this case, your time t for the flow to travel through this will be a big will be quite long. Okay. Okay. Simply because the whole flow is being impeded by this silt layer. Now, let's say the flow is actually going through this direction, this other direction. Sorry. Let's say we have another flow. Let's consider another scenario. So let's delete this flow layers. Okay. Let's consider a flow going parallel to the bedding plane. Okay. These pink lines are the groundwater flow. And notice how the flow paths can actually take up different layers in which they can flow. Therefore, this middle path can basically get stuck up with the silt layer, so it's gonna move very slowly. Okay. Up to the point where it might basically get sort of clogged or sort of get into a traffic jam here through the silt layer. So it can basically divert partially through the more permeable layers, which is the sand. Okay. Okay, and the same case can also happen to the third sand layer. This flow path can easily divert through the faster sand layer. Okay. And this will result in a more efficient flow of water through the bedded layers. Okay. as long as the flow path is parallel to the bedding planes. Okay? Therefore, your time to flow through this layer will be relatively shorter. Okay? And that's how basically anisotropy of flow works in principle. Okay. All right, now let's go back to the concept of seepage velocity and Darcy velocity. Okay. My favorite, not favorite, but my commonly used analogy, okay, for Darcy and let's say, okay. All right, let's say this is your media. Share the screen. Let's say this is your media. You cannot annotate. Okay, this brown thing is your media. Let's say soil. Once your groundwater enters your media, it will have to traverse through the pore spaces within the soil. And we know that the pore spaces within the soil do not form a straight line. Therefore, the flow path here inside will have to take some tortuous or contorted flow path lengths. No? So they will have to literally snake through the pore spaces. Okay? Okay. And if you actually measure the whole length traveled by these flow paths within the media, it will be relatively long if you have to stretch out the whole total length traveled by these flow paths. Okay. And this is what we call, so if you measure this whole line traveled by the flow path, and then you divide it by the time taken to travel that would be your seepage velocity. Total uh length traveled divided by time equals seepage. Okay. So we also call this a 3D velocity. Informally call this a 3D velocity. Now, we also have another concept called the Darcy velocity, where we only care about the net movement of the whole group of groundwater flow through the media. So you can actually have various flow paths within the media, and they can go through so many directions. But in the end, if you're talking about Darcy velocity, you only care about the movement of the flow front. Okay, you only care about the movement of the whole group, okay, in general. So this is the only part where you care about. You only care about the whole flow front moving. So you just measure this part and then divide it by the time needed to travel. So you have this flow front movement length divided by time. That's your Darcy velocity. Okay. My analogy for this concept is you can look at a group of flies. Okay. So each individual fly will move on an orbital direction. Okay? It can move in a very, very twisted direction. Okay? And this other fly can also move through this direction. But as a whole, they can move. So they can actually move or fly literally very fast. Okay? Because they're moving through a circular or maybe a twisted direction. But as a group, they actually might be moving slowly. Okay? So the individual movement of the flies is similar to the seepage velocity. Okay? So they can move very fast. Okay? And if you will just look at their individual movement paths, they can actually move very fast. But if you look at them as a group of flies moving at a certain direction, they might actually be moving very slow as a group. Okay? And that is analogous to the Darcy velocity. Okay? All right. Okay. So naturally, the seepage velocity will always be faster than your Darcy velocity. Okay? And we normally relate the seepage velocity to the Darcy velocity using the effective porosity. Okay? So the relationship here is that the the lower the porosity, the tighter the spaces are for the groundwater flow paths to go around. So the tighter the space, the faster they have to go in order to cause some net movement. Okay? And you can see here your VS, your seepage velocity, is equal to your VD, your Darcy velocity, divided by your effective velocity. Okay? This is your seepage velocity. This is your Darcy velocity. For now, you can ignore this part. And this is your effective porosity. Okay? So if you have an effective porosity of 0.5, your seepage and you have a Darcy velocity of, let's say, 10 meters per second. 10 meters per second divided by 0.5, that will be effectively 20 meters per second. So you are effectively doubling the velocity rate for the seepage velocity. Okay. Okay. Let's continue. And these are the typical values of intrinsic permeability and hydraulic conductivity. For now, you can forget about this part. Just focus on the hydraulic conductivity. This is what you need for this exercise and for the most of the activities in the contaminant in the geoenvironmental engineering course. All right. You can see here that gravel, for example, will have a hydraulic conductivity of. So you will notice that hydraulic conductivity is expressed in centimeters per second in this example. In effect, it's like just a measure of velocity of the fluid, okay, without the modifiers. Okay. Hydraulic conductivity is essentially just a velocity, a sort of a velocity measure for the fluids without the modifiers. We will talk about the modifiers later on. But for now, imagine hydraulic conductivity as some sort of a velocity parameter. All right, for the gravels, you have 10 to the negative 2 to 1 centimeters per second. Therefore, that's something like point 0.01 centimeters per second to 1 centimeter per second. Okay. As you move through the finer soils like sand, you get a progressively slower hydraulic conductivity. In here, you have 10 to the negative 3, so that's like that's 0.0012 point one. Okay, as compared to the previous one. Okay, at least you can see here that going from sand to gravel, there was a decrease in hydraulic conductivity by a factor of 10. Okay. Now, as we move to silty sand, you get something like -5 to -3. Okay. If you look at this one, that's like you essentially decrease the velocity by a factor of 100. Okay. And then from silty sand to silt, again, it's another fact. You essentially decrease the hydraulic conductivity by a factor of 10. And then again to clay, you again decrease the velocity by a factor of 100. Okay. And those are huge jumps in numbers. Okay. And you can imagine in hydrogeology and in contaminant calculations, a simple mistake in identifying the soil type can result in a very, very huge error in the calculations. Okay? By factor of 10 minimum. A minimum factor of 10 error. Okay? Therefore, hydrogeology and contaminant calculations can be very, very sensitive, and data is very important, especially on-site data. Okay. You can still use some assumptions like book values, but you have to be very, very conservative. Okay, and be very, very careful with your interpretations. Okay. Now, this is another table on how to convert your hydraulic conductivities. Okay. And I will show you briefly how to convert some values using this table. Let's say you start from a 1 meter per day unit and you want to convert into centimeters per second. Okay, basically, all you have to do is multiply this value by this factor. Okay. Okay, so 1 times 1.16 times 10 to the negative 3 to convert to centimeters per second. Now, if you want to go the other way, you want to go the opposite way, from centimeters per second to meters per day, you basically have to multiply 1 centimeters per second and multiply it by 8 point. Yeah, just have to multiply it by 8.64 times 10 to the negative times 10 to the positive 2. Okay. And then from feet per day, sorry, from feet per day, to, let's say, centimeters per second, you just have to multiply it by, you just draw a straight line here, feet per day. And then if you want to convert it into centimeters per second, you basically just have to use this multiplication factor. Okay. All right. So basically, you just have to draw a line to whatever value you have, and then draw another line for the value in which you want to convert to. Okay. And then Darcy's law, basically it's just an equation. It's not a law. It's just a equation that says that your discharge Q, or your volume of flow per unit of time, is just equal to your hydraulic conductivity multiplied by your modifier, which is your hydraulic gradient. Okay. This is the modifier that I was talking about earlier, your hydraulic gradient. Okay. And you can imagine that the higher the gradient or the steeper the gradient, you get faster velocity. Okay, that's basically how the hydraulic gradient works. The steeper the gradient, the you get faster velocity. Okay. Therefore, this charge is just equal to hydraulic gradient multiplied by your hydraulic conductivity and then multiplied by the cross-sectional area of the flow. Okay. Or basically the cross-section of the flow front. Okay. Right? Hey, now you have your first tutorial for this exercise. You have a landfill. Okay, this is your garbage or the landfill. And sorry. Okay. This is your landfill. And you can notice some red line here. That is your essentially your garbage juice, or we call leachate plume, your leachate. And in this scenario, unfortunately, there was a leak in the landfill. Okay. Basically, landfills should be designed to be either leak proof or very, very impermeable. But in this case, somehow we have a leak from the bottom of the landfill. And it's actually going down into the aquifer below the landfill. Okay. And you can see here the blue line, which is the flow direction of your groundwater. And then you have this dashed gray box, which represents the cross-sectional area of the aquifer. All right. Let's go again to the given. You have leachate leaking into a landfill. And the leachate basically has merged with the groundwater. So you have a dissolved plume. And your data is as follows. You have a cross-sectional area of the plume, or the cross-sectional area of the flow is 100 square meters. Okay. And then your groundwater gradient or your flow gradient is, or hydraulic gradient is 0.005. And then your hydraulic conductivity is 1,000 gallons per day per square feet. Okay, so this is a valid hydraulic conductivity unit, but we're just using American units because that's what's given in the textbook. Okay. Now for the solution, or rather the question, or the objective here is to estimate how much fresh water is actually entering the contaminated zone. Okay. So this is your contaminated zone. This is your fresh water entering the contaminated zone. And the question is how much water, how much volume of water is actually entering this contaminated zone per day. And the solution is as follows. You basically have to convert your hydraulic conductivity from your ridiculous American units, this atrocious unit of measurement. You have to convert it into a more superior unit, which is your meters per day measurement. Okay? Therefore, 1 gallon per day, 1 gallon per day per feet squared, you have to convert it into meters per day. And you can basically just use this table provided. Let me do that. Okay. Again, what I taught earlier, just start with the rows in here. And our starting unit of measurement is gallons per day per feet squared. Okay. Just draw a horizontal line, okay, through here. And then just look at the target unit of measurement. We need meters per day, so we just draw another set of line going through here. And you can see here, this is the conversion factor that we actually need. It's 4.1 times 10 to the negative 2. So that's 0.042. Okay. This is 0.041. Oh, sorry, 0.041 as shown in here. Okay. Therefore, to convert your 1,000 gallons per day per feet squared, you just have to multiply it by 0.041 meters per day. And you will get something like 41 meters per day hydraulic conductivity. Now, the second step is to calculate your discharge using your Darcy's equation, which is your discharge is just equal to your hydraulic conductivity multiplied by your hydraulic gradient by the cross-sectional flow area. And your hydraulic conductivity is 41 meters per day. And then your gradient is 0.005. And then your cross-sectional area is 100 square meters. That will give you 20.5 cubic meters per day. Okay? And that is the amount of fresh water entering the impacted zone per day. Okay? And then for the actual exercise, this is what you should be solving for the actual problem. Basically the same situation, except that you have slightly different parameters. Okay? So you basically can just refer to this tutorial problem when you're solving this actual exercise problem. All right. Now for tutorial number, this is tutorial 1. This is tutorial 2. Tutorial number 2, again, you have your you have your landfill in here. And you have your leachate. And then you have what we call your compacted clay liner. This compacted clay liner, it serves one purpose. If you will actually go back to this table of hydraulic conductivity, you will see that clay has the lowest hydraulic conductivity possible for all the soils. It's basically 10 to the negative 9 centimeters per square to 10 to the negative 6 centimeters per squared centimeters per second. So you can imagine you will need like 1 million seconds to travel 1 centimeter. So you can convert that 1 million second to days. Okay. So clay, for example, will need like 11 days to travel 1 centimeter. Okay. That's the upper bound of the velocity of the clay. If you're using the lower bound, which is the negative 9, you can go like 1 billion. Okay. You'll basically need 11,000 days to travel 1 centimeter. Okay. Or you can also convert that into years. Or basically, you will need 31 years to travel 1 centimeter if your clay is very, very, very impermeable. Okay. So that is really, really slow because most landfills will typically have a design life of like 25 to 50 years. Okay. So 25 to 50 years, you can imagine that by the time your leachate has traveled 1 centimeter to the compacted clay liner, the landfill is already about to be decommissioned or already about to be rehabilitated or whatever. Okay? Therefore, you can see that clay, okay, has a very, very special value for landfills. It has a very, very low very, very low hydraulic conductivity that it can essentially hinder the movement of contaminants or leachates from the landfill. Okay, hence your compacted clay liner. Okay, okay, you have your given, you have your CCL or compacted clay liner at the bottom of the landfill. The thickness of the CCL is 2 meters. Okay, go back to the whiteboard. Oh, sorry, screen. Thickness of the CCL is 2 meters. And the CCL has a hydraulic conductivity of 10 to the negative 7 centimeters per second and an effective porosity of 0.2. Okay. Due to the leachate accumulation, you have a very, very thin layer of leachate. Okay, less than almost 0 meters thick at the top of the CCL. And the leachate will eventually seep down through the CCL. Essentially, your problem here is that how much time will it take for this leachate to travel from this top of the CCL to the bottom of the CCL. Okay. Okay, how much time will it take the leachate to travel through the CCL vertically? Okay. So assume that the landfill has a very high hydraulic conductivity and assume that the travel time from the top of the leachate to the bottom of the leachate is negligible. So essentially, you can just consider the leachate as a thin line and the travel of the leachate from this part is negligible. So you're only concerned about the leachate traveling from this point to this point. Okay. From top of the leachate to the bottom of the CCL. And these are the questions. First, you have to determine the hydraulic gradient, then determine the Darcy velocity, and then determine the seepage velocity, and then determine the time for the leachate to travel through the compacted clay liner. All right, for calculating the hydraulic gradient, you basically have to divide the hydraulic head loss by the flow path length. Okay. In this problem, this is what we call the head loss. Okay. Okay, let's draw a purple line representing the flow path here. Okay. It's a nearly vertical flow. Okay. As you can see here, it's actually a vertical flow. And the head loss is basically, so you're going from point A to point B. And the head loss is basically the vertical, or basically the change in elevation from point A to point B. That's your DH, or your head loss. Okay. We don't know the exact elevations of point A and point B, but we know the difference in their elevations because we know the thickness of the CCL is 2 meters. Okay? Therefore, we can conclude that the head loss is 2 meters. Okay? This is the vertical. That's a change in the head, hydraulic head. Okay? We also have to know the flow path length. Okay? In this case, normally the flow path length, it's commonly a horizontal line. But for hydrogeology, the flow path length is essentially just the straight line direction of the flow path. Okay? So for example, if you have a flow that is diagonal, okay, the head loss would be this vertical component, that would be your DH. And then the flow path length would be this straight line distance, okay, which is the length of the diagonal line. Okay. Now, in the case of our exercise, the vertical, this is your head loss, the vertical line, the vertical change in elevation. And incidentally, the straight line is also this one. Okay. And we know that the CCL, or essentially the straight line of the flow path, is just same as the vertical line. And we know that this distance is just again 2 meters. Therefore, the DL, or the flow path length, would be still 2 meters. Okay. Right. And essentially, hydraulic head difference is 2 meters. Flow path length is 2 meters. Therefore, your hydraulic gradient is just 2 meters divided by 2, and that's equal to 1. Okay. Now, for the Darcy velocity, Darcy velocity is essentially just your hydraulic gradient multiplied by your hydraulic conductivity. So hydraulic conductivity K multiplied by I, your hydraulic gradient. Okay. Hydraulic gradient was given in the problem. So it's 10 to the negative 7 centimeters per second. And then you just multiply it by 1. And you will get 10 to the negative 7 centimeters per second. Okay. And that is still a very, very slow movement. Okay. So that's around 100 million. No, 10 million seconds. And okay, so that's about, you need like 115 days to travel 1 centimeter, or about 4 months to travel 1 centimeter. That's how slow the compacted clay liner is. Now, we actually have to calculate the seepage velocity here, not the Darcy velocity, because as I discussed earlier, seepage velocity is a faster velocity, okay, compared to the Darcy velocity. Okay? And you can imagine if this is your compacted clay liner, okay? You can visualize the Darcy velocity as this part, okay? It's the group movement, okay? So you can, but in reality, you can actually have a leachate that's actually moving very, very fast individually. And then the rest of the leachates are moving quite slowly, okay? And if you will look at this from the Darcy velocity perspective, this group might actually appear to be moving very slowly. But if you will look at it from the perspective of seepage velocity, it is possible that you might have some of the leachates moving quite fast and quite directly towards the bottom of the CCL. So in short, the group movement or the Darcy velocity of the leachates might be slow, but you might have some leachates or strings of leachates that might be moving faster, okay, individually. And that would still be a concern in terms of contamination. And that is what you would want to know. Okay? What is the earliest time in which the leachates would arrive at the bottom of the CCL? Okay? And you can determine that by using the seepage velocity, not the Darcy velocity. Okay? In short, seepage velocity will give you the first arrivals, the fastest times in which the contaminant will reach a certain point. Darcy velocity is good for determining the overall movement of the whole contaminant. It's only good for volume estimations actually, but it's not good for knowing the timings of the contaminants. Okay? That's why we are calculating the seepage velocity for this problem to know the first arrival of the seepage of the contaminant into the bottom of the CCL. And to do that, you have to convert your Darcy velocity into your seepage velocity. And you can easily do that by dividing your Darcy velocity by the effective porosity. And the given effective porosity is 0.2 as given in this problem. And that will essentially increase, you'll get a seepage velocity that is 5 times higher than your Darcy velocity. Okay. And then after that, to calculate the time needed for the leachate to travel to the CCL, you just have to divide the flow path length by the seepage velocity. And that would be 2 meters divided by 5 times 10 to the negative centimeters per second. For convenience, you can convert 2 meters into centimeters. So that's 200 cm. And you will get like 400 million seconds. Okay? Or that will be approximately 12.7 years. Okay? Okay, that's like 12.7 years for the CCL, for the leachate to travel to the CCL. In the perspective of landfill design, again, the typical life of a landfill will be somewhere between 25 to 50 years. Okay? And getting a leak within the first 12 years would be a problem for the landfill. Okay? And for example, you might have to redesign the CCL, or you might have to do some mitigation measures for the landfill. Okay? So this is not acceptable in the perspective of the landfill design life. All right. For the problem, again, you have basically a very similar setup, but just different parameter values. Okay. Okay. Now let's move to tutorial number 3, which is basically the same, very similar setup. Okay, zoom back in. Wait a minute. All right, let's resume. Sorry for the interruption. Mian, can you hear me?
Opo, sir.
Okay, thank you. All right, tutorial number 3. Basically the same situation as in the second tutorial, except that you have a thunderstorm. Okay, and it caused a rise in the leachate thickness. Okay. Actually, by design, the landfill should have a cover from the surface. Okay. There should be some sort of a tarpaulin or an impermeable cover, so that in the event of thunderstorm or rainfall, there would be a minimal amount of water entering the landfill. Although in this case, there was like a severe storm, so you still had an accumulation of water, and therefore an accumulation of leachate in the landfill. All right. The consequence of this accumulation of water is that you actually have now a higher hydraulic head acting at the CCL, no? So you can imagine this as you have a higher pressure of water that's trying to force its way down to the compacted clay liner. Okay. Okay, again, you essentially have the same parameters except that your leachate now has a thick layer about 3 meters thick above the CCL. Okay. Now you can again start with the hydraulic gradient calculation. And hydraulic head difference is just the top of the leachate water to the bottom of the CCL. So you can imagine it like this. Sorry. Essentially, this leachate has a thickness of 3 meters. The CCL has a thickness of 2 meters. Okay. And now our problem is actually going from point A to point B. Okay. And you will notice here that you now have a higher drop in elevation going from point A to point B. Okay. Again, you don't know the exact elevations of the 2 points, but we know the relative change in elevation, which is indicated by the thickness of the leachate and the thickness of the CCL. That is basically 3 meters plus 2 meters. Okay, therefore, the hydraulic head difference is just 3 plus 2 is equal to 5 meters. Now, the flow path length is quite different. It would be quite different now. Okay. Normally, we would consider the DH as 5 meters and the DL as also 5 meters normally. Okay. This is the most simple way to look at this, but if you'll go back to the problem discussion, we have to assume that the hydraulic conductivity of the landfill or this part is actually negligible. So therefore, you can actually split this into A1, A2, and then B1. So this segment, the travel time for this segment is actually almost zero. It's negligible. While this part is a very, very long travel time. So essentially, we can just, for the flow path length, we can just ignore this segment. Okay. We can ignore the segment of travel to the leachate. And therefore, we can just consider the thickness of the leachate. Therefore, the DL will be just 2 meters. Okay. So we still can't, even though the flow path length that we're concerned with is just this one, we cannot just disregard this vertical column of water that's exerting pressure at the top of the CCL. So the DH will still be this one. This will still be the DH, while the DL will be just the leachate thickness. Okay? So DH will still be 5 meters and the DL will be only 2 meters. Okay? Because we have to ignore, or we can safely ignore the travel time to the leachate. Okay? All right. Now, that will lead us to a hydraulic gradient of 5 divided by 2 meters. So the hydraulic gradient now is 2.5. So it's quite high. Okay. And essentially, that's the only parameter that changed throughout the problem. Okay. You increased the hydraulic gradient because you added a surcharge of water here. No, you have a thicker leachate thickness, and it's essentially exerting more pressure at the bottom, at the top of the CCL. Okay. And you essentially, yeah, you went from a hydraulic gradient of 1 in the first problem to a hydraulic gradient of 2.5 simply because you have more hydraulic head difference. Okay. And as expected, you will essentially have a hydraulic you'll have a Darcy velocity that is 2.5 times faster and a seepage velocity that's also 2.5 times faster and a travel time that is about smaller by a factor of 2.5. So you only take now 5.05 years for this leachate to pass through the CCL. Okay. All right. What I did here is just I demonstrated how an increase in the thickness of the contaminant or an increase in the hydraulic head can actually affect the velocities of the contaminants or the groundwater. Okay. Essentially, the time was essentially more than half. Okay. Okay, and that again is a problem. Okay, in the perspective of your landfill design. Okay, either so on top of actually mitigating the CCL in problem one, you may also have to find a way to prevent water from entering the landfill. Okay. But that's just the practical side of the exercise. You don't need to worry about that. For the actual exercise, you just need to solve problem one and problem two, which are basically just duplicates of the tutorial. Okay. All right, let's go now to the third part of the exercise, which is determining the ground water flow gradient and the flow direction. If you did some resource geology or some mining geology subjects, you should have encountered this problem. Have you encountered this problem before? The 3-point problem, Megan? Does this sound familiar to you?
Sir, familiar na po.
Okay, that's good. Okay, 3-point problem, you have 3 points, or actually minimum of 3 points with different elevations indicating a sort of a contact, like a bedding plane. And then from those elevations of bedding planes or geologic contacts, you want to determine the strike and dip of the bedding plane surface. Okay. In the case of groundwater flow, you can imagine the groundwater is actually not a flat surface. Groundwater actually has an inclination. Okay? Groundwater basically is always inclined. That's why it's flowing. So groundwater will essentially just imitate the underlying topography for most cases. Okay. All right. You can see here the groundwater will have an inclination and will have a direction. And it will always flow from the higher elevation to the lower groundwater elevation. Okay. And we need that for the contaminant calculations because that will tell us where the contaminant is actually going. Okay? So it's not too different from the geologic bedding 3-point problem. You just imagine the groundwater as a bedding plane or whatever, or some sort of a contact. All right. Given you have three water elevations determined from monitoring wells, what you did here is you did three drilling wells, and then as per the standard procedure, you have to observe the water level 7 to 2 hours or 3 days after the drilling was finished. Okay. Okay, so this is a standard procedure for drilling groundwater. You have to wait for the water to settle down before measuring its elevation. And that would be safest to be around 72 hours or 3 days. Okay. Remember that once you start doing some actual work involving wells and water. Anyway, going back to the problem, we have three wells. Sorry. You have three wells, and these are the coordinates of the wells. You have X and Y coordinates. And you will need these coordinates to plot them on a map. And then the final column shows your groundwater elevation measured relative to the sea level. Okay. Sea level is usually assumed as zero elevation. Okay. And you have like 2,000, 1,500, 1,000. So this is quite a high elevation. Okay. Now the questions are as follows. You have to determine the groundwater flow direction, the hydraulic reagent, and you also have to estimate the discharge given an aquifer with a cross-sectional area of 100 square meters and a hydraulic conductivity of 10 meters per day. Problem three, you can worry about that later. You can forget about that for now. Let's just focus on problems on questions number 1 and number 2. All right. These are the steps in determining the hydraulic, the groundwater flow direction in the hydraulic gradient. Okay. So this is the text version. This is the visual one. As you can see here, we just plotted the locations of the three wells using their X and Y coordinates. For example, well 1 has a coordinate X equals to 0 and Y equal to 0. And naturally, you will have well 1 at the origin. Okay? X is equal to 0, Y is equal to 0. So it's just located at the origin. This is well 1. Well number 2 has an X value of 100 and a Y value of 100. Right? And basically, Y equal to 100 is this one. X equal to 100 is this one. So X and Y in here, you will. So this is this is Y is equal to 100. This is X is equal to 100. So therefore, you will be plotting well 2 about in this area. Okay, this is well 2. This is well 1. And then well number 3 is you have an X of 0 and a Y of 100. So X is 0, so it's just gonna be plotting around here. and then y is 100, so it's gonna plot around this location. Okay, that's step one. We just plotted all the locations of the wells and indicated the elevations of their groundwater levels. Okay, that's step one. Step two is easy. You just have to draw straight lines connecting all the wells. Okay. In this case, you only have three wells, so you just have to draw a triangle connecting all of them. Step three is to calculate the elevation difference, okay, between the three wells. For well 1 and well 2, you have 2,000 and 1,500. Therefore, the elevation difference is 500. And then for well 3 and well 1, the elevation difference is 1,000. And then for well 3 and well 2, the difference is 500. Okay. And then the step 4 is actually to calculate the greatest common factor. So I don't know what that means. But the greatest common factor is supposedly the biggest number that can divide all these three numbers. Okay. I think there are methods taught like 10 or 20 years ago when you were in the grade school, but I don't remember them anymore either. So in this case, you can just do by trial and error. At least we know here that the greatest common factor of these three elevations is 500. Okay? So the GCF is 500. That's the biggest number that can divide all these three elevations. And then, so the greatest common factor is 500. And I think step 5 is to look at these connecting lines and subdivide them by the greatest common factor. So in here, at least we know that the difference between well 3 and well 2 is 1,000. Okay. So we know that 500 is located somewhere in between them. Okay. So this is 500. This is 500. And this is 500 because 2,000 and 1,500 it's 500. And 1,000 and 1,500 is 500. Okay. So basically, we only need to subdivide this line. And since we know that this is 500 and this is 500, we also know that the elevation of this point of this midpoint would be somewhere between 2,000 and 1,000, which is 1,500. Okay. After subdividing the connecting lines into the GCF, we just have to connect the points with same elevations. In this case, we only have 1,500 in this point and 1,500 in well 2, so we just connect them together. But for the purposes of locating the actual flow direction, we will need more lines actually. So we can actually use a smaller GCF, which would be 250. And further subdivide these lines by 250. So what's gonna happen is that this midpoint here would be, this is 250, this is 250. Again, this is also 250. This is also 250. This is also 250. So this would be 1,750. this would be 1750. And then this point would be 1250. And this point would be 1250. Okay. After that, we just need to connect them again. So you have your smaller subdivisions being connected together. So again, note that I just connected the elevations with same values. So 12 to 12, 17 to 17. And it should look like something like this. Okay. And now what we essentially did is we just made what you call your contour lines. Okay, you have contour line one here, another contour line here, and a third contour line in here. Note that these lines are useless. These other lines are useless because they do not actually mean anything. So we only focus on these three contour lines. Okay? And from at this stage, it's actually apparent where is the higher elevation of the groundwater. It is actually here. And this is the lower elevation. Okay. And we know that groundwater will always flow from the higher elevation to the lower elevation. So you can essentially just draw a perpendicular line going across your contour lines. Okay. Therefore, Mayan, what do you think is the direction of the groundwater flow? Is it going north? Is it going east? Mayan, what do you think is the direction of the groundwater flow based on the arrow? Okay, I think you're not yet ready to answer. Anyway, the direction of the groundwater flow was based on the elevations. Okay, and the arrow that we drew across the contour lines, it's just going into this direction. It's going somewhere north and somewhere to the west. Okay, so it's going northwest. Okay. So you have a northwest groundwater flow direction. Okay. So at least now we know the direction of the groundwater flow. If there are contaminants in this groundwater, they will also follow the same direction as the groundwater flow. Now we can go to the other steps. So it's northwest. Now, the beauty of this diagram is actually, if you're familiar with interpreting the topographic maps for elevations, we know that you can calculate the topographic slope by simply measuring the horizontal distance between two contours. Okay? So you just have to measure the distance between the two contours. In this case, this is like 22 meters. And then you just have to get the hydraulic head difference, which is essentially just the difference between the two contour lines. Okay. And in this case, the hydraulic head difference is just 250 meters. And from there, you can calculate the hydraulic gradient, which is just 250 divided by 22 meters. You will get 11.06. Okay. And given that, since you already have your hydraulic gradient, you can now go to your problem number 3. the tutorial, which is this one. Problem number 3 is determine the discharge. So you just need to multiply the hydraulic gradient, which is already given. It's 10 meters per day. Multiply it by the hydraulic gradient, which is 11.06. And then multiply it by the cross-sectional area, which is also given, 100 square meters. And you will get 11,000 cubic meters per day of discharge. Okay. For the problem, again, you have very, very similar situation, but with slightly different values. Okay. All right. At this point, I will only require you to solve up to this problem. Okay. Chapter 5, I won't be requiring you anymore to solve chapter 5. Just gonna draw this one. Okay. Okay, is that clear? I mean, you only need to solve the problems in this exercise up to chapter 4. Okay, I won't be requiring you to solve up to this part anymore. Okay. So you can just focus on these problems. Is that clear?
Opo, sir. Yes, sir. Clear.
So this exercise will now be only worth like 6. So I will have to reduce the maximum score by 12 points. Okay, so I'm just gonna save this document. And upload it on Blackboard. Mm, okay, so far, do you have any questions?
Sir, are you going to upload also the recording?
Of
Nito?
course.
Okay.
The grade is so this is just gonna be maximum of 38 points. Okay. Right. So if you have no other questions, thank you for attending this tutorial session. Okay. Right. Thank you for attending, man, and see you probably in the next 2 meetings. Okay.
Okay
Have
po.
a good weekend. Okay, and yeah, see you around.
Thank you po,